we've looked at the left-hand side of the standard model of elementary particles, so the fermions that consist of the quarks and leptons. We're now going to look at the right-hand side, being the bosons. We'll start first of all looking at the gauge bosons, and then we'll deal with the scalar boson, the Higgs boson, in a later video. Now, in order to talk about these gauge bosons, we actually need to also talk about fundamental forces. Now, current theories of our understanding of how everything around us behaves and interacts identify four fundamental forces, and so these four fundamental forces are the forces that basically keep everything together, govern the interaction of the particles that we're dealing with here, and then anything that's bigger than that that's made of those particles. Note that the word here, theories, doesn't mean a guess. Quite often in everyday usage, a theory is sort of a hunch or a guess. In a scientific context, a theory is something that's been tested, evidence has been found to support it through repeated experimentation, and so it's not that we're guessing here, it's that we've got lots of evidence to identify that these forces exist. Now, each force that we're dealing with here is mediated, and by mediated what we kind of really mean there is that it's transmitted by a gauge boson. Now, a gauge boson, or the bosons in general, are a bit of an unusual one to get your mind around, so we'll talk about what they are and how they behave, but in the end it's one of those situations again where you just need to be able to identify which gauge boson mediates which of the fundamental forces. Now, to take this a step further, this is not something that you need to know, but just to clarify, a boson basically has a zero or integer spin, so whole number integer spin, compared to fermions that have a half integer spin. So that's the difference between bosons and fermions. In the same way that we had fermions that were composite particles, there are some bosons that are composite particles as well. So anything that's got an integer spin or a zero spin would be a boson. So mesons, for example, are bosons because they have that integer spin. We're only really concerned here with the fundamental particles, so we don't need to worry about bosons that are composite particles. We only need to worry about these four that we can see in the standard model. Now, in order to sort of summarize these forces and the bosons that mediate them, just going to sort of tabulate a whole lot of information here. Hopefully I've left myself enough space in this grid. So we're going to have we'll look at the force sort of across the way, and then we'll sort of deal with all of the things that we need to consider about those forces. So the first then is going to be the strength. The second will be the range over which it acts. The particles that the force acts on, the mediating boson, so which boson relates to which force, and finally we'll just summarize some of the roles that those forces have. So first of all, the first force we're going to deal with is the gravitational force. The second that sort of is another one that we've already seen and a little bit easier to relate to is the electromagnetic. And you'll see why I'm putting that one in the third column as we go through. The next one then is the weak nuclear force, and finally the strong nuclear force. Now, the reason why I've written them in that particular order relates to the strength. So we can basically identify that as we move across the table, we have increasing strength. Now, we could quantify how big that increase is for each one. I'm not going to really bother going into that much detail, but a couple of notes to make along the way though. The first is that the gravitational force is dominant over astronomical distances. So when we're dealing with anything that's very large, so between galaxies or between stars, the gravitational force is the one that is the most dominant. Even though it's a very weak force in comparison to the other three, it's the one that is still measurable over those sort of distances. On the flip side though, if we go to the very small, the gravitational force is negligible. So it's negligible on atomic or subatomic scales, and subatomic scales. So it's a bit of an unusual one compared to the others. One of the current areas of research in physics is trying to actually link gravitational forces in with the other three. So looking for a unified theory that basically sort of groups all these in a way that they look like they're all basically representations of one single force. Now if we skip across to the electromagnetic, that's now, if we look at the electromagnetic force, it's much stronger than gravity over short distances. And finally, the only other thing that we'll need to write here is that the strong nuclear force is very strong. Now, in order to sort of state exactly how much each one, how strong each one is, you kind of need to have a comparison across different distances, and over different distances the forces will vary. So there is an example in the textbook that we might have a quick look at, but that's very specific to the interaction between two protons. So depending on the particles that are involved, the strengths there are going to be sort of different scale factor differences between them. Now, if we look at the ranges of these forces, we're basically saying how far a distance can these forces act. So first of all, for the gravitational and electromagnetic force, they can act over infinite distances. So any two masses over an infinite distance could experience a gravitational force. Obviously it's going to be very weak over larger distances, but ultimately it can still act over an infinite distance. As we go sort of the other way, if we get smaller and smaller, the range of the strong nuclear force is in the vicinity of 10 to the negative 15 meters, whereas for the weak nuclear force it has a range of 10 to the negative 18 meters. So you can see there the weak nuclear force acting over a shorter distance. The other interesting thing to notice about these forces that I haven't really left space for here, but with the gravitational force, it's always going to be attractive. So you'll always have an attraction when you're dealing with gravitational forces. With electromagnetic forces, they can be repulsive or attractive. With a strong nuclear force, at that sort of range of 10 to the negative 15, it tends to be very attractive. At shorter distances than that, though, it tends to be very repulsive. So 10 to the negative 15, very attractive, but then becomes a very repulsive force as it gets to much shorter distances than that. Now, the particles that the gravitational forces act on are all particles. So every particle is going to experience a gravitational force. The electromagnetic force, we'll just jump across to that one first. As we've already seen, that's going to act on charged particles. So any particle that has a charge is going to experience the electromagnetic force. So protons, electrons, tau particles, anything along those lines. Anything that's neutral, so neutrinos, a neutron, or some of the other hadrons that we've seen, will also not experience the electromagnetic force if they are neutral. Now, the weak nuclear and strong nuclear forces, they're both going to act on quarks to begin with. The weak nuclear force also acts on leptons. The strong nuclear force acts on quarks and gluons. Now, gluons, as we know, are a mediating boson, and the gluons actually are the boson that mediates the strong nuclear force. The weak nuclear force is governed by the W+, W-, and Z bosons. So in our table above you saw that the W and the Z were listed there. So the W can actually be grouped into two because they have charge. So W+ having a positive charge, W- having a negative charge, and the Z boson having neutral charge. The electromagnetic, is mediated by the photons, so basically packets of energy. And finally, the mediating boson for gravitational force is the graviton. You'll notice that that's not actually in the standard model. So this particular boson, it's been hypothesized to exist, but we are yet to actually confirm that it does exist. There's no experimental evidence to indicate that gravitons actually exist. Now, just to finish up the roles of these particular forces, we kind of already know some of them. So with the gravitational force, it's about binding planets, stars, solar systems, galaxies together. So any of those large astronomical bodies are kept together thanks to the gravitational force. If we go across again to another one that we've seen, the electromagnetic force is responsible for binding atoms together, and it's also responsible for creating magnetic fields. So the creation of magnetic fields is due to the fact that charged particles have a spin, and that spin causes the generation or the creation of a magnetic field. As you might be able to guess, the strong nuclear force is responsible for binding the binding nuclei together, and it's also then responsible for nuclear fusion. So keeping the smaller nuclei, when they fuse together, keeping them together. Finally, the weak nuclear force is responsible for radioactive decay. So the transmutation of elements from one to another. It's also involved in neutrino interactions. And the last thing to be aware of here is that it is also responsible for supernova of stars. So there's the summary then of the fundamental forces, some of their properties, some of the important aspects to consider, what they act on, mediating bosons, and so on and so forth. If you look in the data book, you'll notice that some of that is already included. So for example, if I just go through and highlight obviously the top row indicating what each of the forces are, also indicates what the forces act on. So need to know what, in particular, what the forces, what particles they act on, and finally the mediating boson as well. So they're the things that are in the data booklet that you can just look up. You don't have to memorize those, but over time, if you're using these terms quite regularly, you will find that you do start to remember which is which. But there's the detail that's actually in the data booklet itself.